Alright, in this video I'll answer number 33 in section 9.6, partial orderings. The problem statement says, answer these questions for the partially ordered sets 3, 5, 9, 15, 24, 45 on the divides by relation. That's this bar right here. So basically that relation says 3, for example, or 9, for example, is divisible by 3. 24 is also divisible by 3. 15 is divisible by 5, and so on. So we'll start by taking our partially ordered set, and we'll draw a Hasse diagram. We'll start with the lower numbers. Let's do 3 and 5. And we'll see what 3 and 5 go into and draw those numbers above it. So we'll put our 24 over here. Since 3 goes into 24, we'll put a 9 above our 3, the 15 above the 5, and the 45 above the 15. Now from here, we'll just go ahead and make our dots and draw lines for each of the relations. So 5 goes into 15, 15 goes into 45, 3 goes into 9, 3 goes into 15, and 3 goes into 24. So this is the Hasse diagram. Actually, 9 also goes into 45, 5 times. So this is the completed Hasse diagram. So you'll notice we have 24 kind of off to the side. 3 is the only number that goes into 24 in this set. So now that we have the diagram, we can actually answer some questions about it. So the first one would be to find the maximal elements. Alright, so our maximal elements in the partially ordered set in this Hasse diagram will basically have nothing above them. So in this case, the 24 doesn't go into any other numbers in the diagram, and the 45 doesn't go into any other numbers in the diagram. But every other number, say 3 goes into 24, 9 goes into 45, 15 goes into 45, 5 goes into 15, and so on. So 9, 3, 5, and 15 are not maximal, but 24 and 45 are both maximal elements. So maximal elements, 24 and 45. Alright, so the next question would be find the minimal elements. So the minimal elements will be at the bottom of the diagram, and they will be elements where there's nothing that goes into them. So 3 and 5 both are at the bottom of the diagram. There are no other elements in this diagram that go into 3 or that go into 5. So minimal elements are 3 and 5. Next, is there a greatest element? So the greatest element would be literally the very top of the diagram, but only if there's a unique maximal. So here we have 2 maximal elements, 24 and 45. So right now there's not a greatest element because we have 2 maximals. We have to have just one maximal for it to be greatest. So in this case, no, there's no greatest element. So no greatest element. Let's see. Is there a least element? So kind of the other side of this, the least element would only be there if you have just a single minimal element. So in this diagram we have 2 minimal elements, and for there to be a least element, there has to be exactly one minimal, basically that would go into every single number And since there are two minimals, we have no least element. So no least element. If we had a 1 in here, then 1 would be the least element, because 1 would go into the 3 and the 5, and there would be nothing under the 1. But in this case, there's no least element. Alright, next, find all upper bounds of the set 3 and 5. So if they give you the sets 3 and 5, so you want to look at these elements in the diagram, 3 and 5, and you want to figure out the upper bounds. Alright, so to find the upper bounds, basically in this example we'll find a number in a diagram that is divisible by both 3 and 5. So if we look at the diagram, we have 15, which is divisible by both 3 and 5, and we also have 45, which is divisible by both 3 and 5. So in this case, 45 and 15 are the upper bounds. Alright, so next, find the least upper bound of the set 3 and 5, if it exists. Alright, so the least upper bound, basically you would look at your upper bounds that you found, and you would want the smallest one in that particular set. So we have 45 and 15 are the upper bound, so the least upper bound would be 15 actually. Least upper bound 15. Alright, next, find all lower bounds of the set 15 and 45. Alright, so we've got 15 and 45. Lower bounds. Alright, so basically we'll look at these two and see which numbers go into both 15 and 45. So if we look at the diagram, we have 5, we have 3, and 15 actually. So all three of these numbers go into 15 and 45 to some degree. So the lower bounds would be 15, 5, and 3. Now, what is the greatest lower bound of 15 and 45, the set 15 and 45? So basically you would look at the lower bounds that you gathered up, 15, 5, and 3, those are the ones that you found, and you would look at the greatest one of that particular set. So the greatest of the lower bounds that we found is 15, so 15 would be the greatest lower bound of 15 and 45 in this diagram here. So greatest lower bound of 15 and 45 is 15. And that concludes everything for this problem.